Today we tackle antiderivatives. Okay, we're going to introduce you to an idea of antiderivatives and the idea of something called indefinite integration. Indefinite integration. Later we'll talk about definite integration. Okay, indefinite means not precise, not exact. Okay, definite means exact, precise. Okay. All right, so we'll start out with this idea. What is an antiderivative? What does it sound like it is? Okay, so a derivative is when you do a certain process. An antiderivative is going backwards. Okay, so an antiderivative, take a look at this first function. F of x equals 3x squared. Can you name a function whose derivative is 3x squared? What function has a derivative that is 3x squared? X cubed. That's it. X to the third. No, it's the same thing. X cubed. Okay, this is called the antiderivative. Oops. Okay, and we indicate that with a capital F. Okay, sorry, having technical difficulties. All right, we indicate that with a capital F. Now, is x cubed the only function whose derivative is 3x squared?
No.
What else?
X cubed plus 1 plus 2
plus 1. X cubed plus 2. X cubed plus pi. Right? All of those are antiderivatives. Okay? So it's really important to be specific with your language. Okay? So you wouldn't necessarily say that x cubed is the antiderivative. It is an antiderivative. It's one of many. Okay? So here's our official definition. A function, big F, is an antiderivative of little f on an interval I if the derivative of big F is equal to little f for all x in I. If big F is an antiderivative, then G is an antiderivative if and only if G has this form. It's equal to big F plus C. Okay, where C is a constant, it's called the constant of integration. Okay, G is what we call the general antiderivative of F. So in this first example, the general antiderivative would be x cubed, okay, and that would be our big F, and then if we add any constant to it, we get our general antiderivative. I'm sorry, no, I said that wrong. Okay, in this example, x cubed would be our f of x. It's an antiderivative, and then as we add to it, we get our general antiderivative. Okay, so for example, if we have little f equals 2x, what function has a derivative that is equal to 2x? X squared. So x squared is an antiderivative. The general family of antiderivatives would be x squared plus c, where c is, again, what's the name of c?
Constant of integration.
Yes, the constant of integration. Okay. All right, so when we write that out, the general antiderivative, that's called the general solution to a differential equation. Okay, a differential equation is exactly what it sounds like. It's an equation that has derivatives in it. Okay, and remember, what is a solution in math? A solution means whatever you need to put in to make the equal sign true. Okay, whatever you need to put in to make the equal sign true. So if we know that the derivative of some function is 3x squared, a solution would be finding what is this function, what is this g, and we just said it. What would it be? X cubed. Okay, so finding a solution means find the g, find the function that makes this true, that the derivative is equal to 3x squared. Excuse me. All right, so simpler one, find the derivative find the function whose derivative is 2x, okay? The general solution would be x squared plus c, okay? In some cases, a differential equation may include a y in addition to x, but it always has to have at least a y prime. Okay, let's look at example 1. Find the general solution for the differential equation y prime equals 2. What is a function whose derivative is 2? That's our f. 2x, that's it. All right, so our general solution,
2x plus c.
good, is f of x plus c, which is 2x plus c. It's not correct without the c. Okay, you have to have your constant of integration. Okay, here is the notation we use when we are dealing with antiderivatives. We got some new weird squiggly things happening, okay? So, and this is where our differentials are important, and they'll make more sense as we do this. So, when we're solving a differential equation in this form, that dy dx equals, that should say f prime. That's a typo. No, wait, I'm sorry. Is it a typo? No, it's not. Okay, sorry. Little f is our derivative, okay, for which the antiderivative is big F, okay. If we rearrange things, okay, again, the Leibniz notation, technically this is not like division and multiplication, but we're going to treat it that way to a degree. So if we rewrite it as dy equals f of x dx, you see how we rearrange there, okay. The operation of undoing the derivative, of finding the antiderivative, is what we call antidifferentiation, also known as indefinite integration, okay? So if I take the integral, that's what we call it, we call it take the integral of both sides, because in math we're allowed to do it whatever we want as long as we do it to both sides, okay? Then that's what I would write, the little squiggly symbol out front. Okay, and by definition, okay, this squiggly means whatever differential you have, find the function whose derivative it is. So for dy, you would end up with just y, okay, and by definition, we've said that the antiderivative of little f, we're going to call it big F. And in order to have a general solution, we're going to have some constant out there. Technically, you would say that you have a constant on this side too, but now you just have two random constants. Lump them both together on the same side and ignore the fact that you have one on this side. Okay?
So this big fx is equals to y. If you ignore the c, they are equal.
But you can't ignore the c.
Oh.
Okay? Y is equal to the antiderivative plus c, okay? So the way we say it is the antiderivative of f with respect to x, because the dx matches with the f of x inside the squiggle there, okay? The f of x here is what we call the integrand, okay? And then dx is our differential. All right, which you are familiar from the previous section. Okay? All right, we're looking at basic integration rules. These are the same as derivatives, just backwards. Okay? So, if we take a look here, the question we're asking ourselves when we look at the inside, what is this called again?
Basic integration.
take a look. What is this called? This thing that I just circled? What is 0 called? What is k? Nope. This is called the integrand. Okay? When we look at the integrand, we're asking ourselves, the derivative of what gives me this integrand? So as we look at 0, the derivative of what gives me 0? No.
Number.
Any constant. Okay? The derivative of a constant is 0. So that's why the integral of 0 dx, or the integral of 0 with respect to x, is equal to c, a constant. Okay? The next one, the integrand is what? K. Okay, so we ask ourselves, the derivative of what, where k is a constant, okay? The derivative of what gives me a constant? Kx, okay? And then we have to add our constant of integration as well. So k is a constant and c is a constant. So the integral of any number, okay, is going to give us that number times x plus c. So what would this be? To what? 2x plus c. You can't. Yeah, you don't know what c is yet. We'll talk about how to find c in just a minute. For right now, c is always c. Okay. The next one, all right, the constant multiple rule. We could also factor out a constant. You'll notice that this isn't actually solving the integral, okay? It's just factoring out the k. That goes back to the same constant multiple rules that we've seen over and over again with derivatives. Okay, same thing with addition and subtraction, same kind of rules we've seen with derivatives, with limits, all of that. And now we get to some of our more fun rules. The power rule, okay? The power rule. Before, right, we were taking derivatives, and we found that the derivative of some x to some n, some polynomial, was equal to what?
Nx to the n minus 1.
You got it. Nx to n minus 1. So let's do a couple, see if we can find a pattern, okay? So x squared, the derivative was what?
2x.
X cubed.
3x squared.
Okay. X to the 4th.
4x cubed.
Okay. Now we want to think about going backwards. Okay, but we want to think about going backwards with just an x term by itself. So we wouldn't want to consider the 2, the 3, or the 4, the coefficients. Okay, we're looking over here at these guys. Okay, we want to treat those as our integrands. Okay, but really we just want to look at these. Okay, so we're asking ourselves the question, okay, the derivative of what gives me just x by itself? The derivative of what gives me just x by itself? We know it's got to be an x squared because we're reducing the power by 1 when we go from derivative down, okay? So we know it's got to be x squared, but if we want to know what is the antiderivative of just x, we've got to know how to deal with this 2, right? Because if it's x squared, we're going to get a 2 out front. How do we get rid of the 2 out front? The derivative of what equals x? We know there's an x squared. What do we do to make sure our derivative doesn't have a 2 in it? We're going to have to divide by 2. Right? Because that's going to give us 2x over 2, which will just be x. Right? Okay. All right. Try it again. The derivative of what will give me just x squared? You got it. And what about x to the third? Okay, you found a pattern. Okay, what do you see in each of these?
Oh, God.
Okay, so when we are solving the antiderivative of x to the n, okay, where x is any power, our antiderivative will always be that power plus 1 divided by the same number, okay? So if it's x to the 1, our antiderivative will be x to the 1 plus 1 over 1 plus 1. So the antiderivative of x is x squared over 2. And then again, always have to have our plus c, our constant of integration, okay? And of course, in this case, n cannot be equal to -1. All right, that wouldn't work out for us, okay? And what is n to the -1? I'm sorry, n equals -1 would be x to the -1. What is that associated with? 1 over x. What's the derivative of what equals 1 over x?
Equals 1 over x is 1. Wait. It's 1.
The derivative of what is 1 over x?
X0.
Ln x. Okay, natural log. Okay. Okay, so let's take a look. Our trig functions are a little bit tricky in some cases. So sine and cosine, again, you're going backwards. So when you take the integral of cosine, you're asking yourself, the derivative of what gives me positive cosine? So in this case, it would be positive sine plus c. And then same thing here, the derivative of what, okay, remember this is my what.
Oh, yes.
The derivative of what gives me sine x, it would be negative cosine, because the derivative of negative cosine will be negative times negative sine. Okay. We can also see these same ones. The derivative of what gives me secant squared. The derivative of what gives me secant tangent. The derivative of what gives me cosecant squared. The derivative of what gives me cosecant cotangent. Okay, so those are all the same rules we've seen before, a little bit backwards. Okay. All right, let's take a look at this example. Describe the antiderivatives of 3x. So the question is, the derivative of what, and it really helps to write it like this, the derivative of what, leave a blank space, is 3x. Okay, we can use one of our rules, okay? The first thing we can do is we can factor out a 3, okay? We can factor out a 3 and say the derivative 3 times the derivative of something gives us x, 3 times x, okay? And ignore the 3's. Okay, so the derivative of what gives me x? Stop and answer the question I'm asking. Okay, the derivative of what gives me x? X squared over 2. Okay, x squared over 2. So now we can plug back in the 3 and know that 3x squared over 2, okay, the derivative of that will give us 3x. Okay, any questions? All right.